Welcome to the Performance Around the Clock podcast. I am Professor Satchin Panda, a scientist in the field of circadian rhythm. In this podcast, I will talk to experts in many different fields about science, health, and human performance. You'll also find out why circadian rhythms is my favorite topic. I hope you enjoy the podcast and thank you for listening. Welcome to another episode of Performance Around the Clock, and I'm super excited to have Dr. Jamie Justice with me today. And Jamie, as she is popularly known, has a long, I wouldn't say very long, but very significant contributions to the science of aging, geroscience, and particularly very important contribution in the sense, what are the biomarkers of aging? What can be used in a clinical trial to see whether a geroprotector or an intervention is actually slowing down aging process? And she has been extremely, she occupies a very important position right now. She is the director of XPRIZE Healthspan. I hope I said that correctly. And she's also an adjunct faculty in Wake Forest University. She was a full-time faculty there, and she was brave enough to forego her academic position and do something that she was always dreaming about, to really see interventions coming into play to increase health span. So welcome, Jamie.
Yes, thank you. It's a great introduction.
Yeah.
Thank you.
So you always talk about health span, and people think about longevity and lifespan.
Yes.
So what's the difference between lifespan and health span?
It's a great question, and one we get often. Is that often when I tell people, even whether it's family dinners or out in public, and they ask what I do, as soon as I say aging, many of them think we're talking about immortality or lifespan, and they get really uncomfortable. And really, when we're talking about health span, it's a different aspect. And so something that's happened, really the result of great public health measures, right? So anything from clean water, better nutrition, maternal care, is that over the last 100 years, we now live over 30 years longer than humans ever have. And so we already have an extended lifespan compared to previous generations of humans. So what has happened that is not great, and again, those are gifts of years that we now have the opportunity to live that we've never had before. But we don't necessarily live those years well. And so the concept of health span is really looking at those latter years where there is a decline in health, more chronic disease, greater disability, and that essentially we're not fully living the days that we have. And so when we're talking about health span, we're looking for interventions or therapeutics or any strategies, whether it's public health or drug related, anything in between, that can actually begin to address the complexity of aging so that we can live better longer. And if that one day may result in additional years, who knows? But for most of us that are working in this health span space, that real focus is on how do we stay productive, active, and healthy so that we can enjoy the years that we have, regardless of how long they are.
Yeah, so actually that reminded me, like we're talking about longevity these days, but
Yes.
And we always talk about how average lifespan was, say, 40 years or 45 years, 100 years ago.
Yes.
But if we go back, really way back in history, even some Egyptian kings lived to the age of 80 or 90.
That's right.
So that means there are very few, select fews, who may have had all the health care and all the care to actually live a long, healthy life. But biomedical research in the last 100 years kind of democratized that public health.
That's
so that
absolutely right.
You don't have to be Egyptian king or in the royalty to actually benefit from a long lifespan. And that's very
right.
good. So you said that every year of biomedical research in the last 100 years has added 0.3 years. So that's around 4 months, 3 to 4 months to human lifespan. And along that metric, how long have we added to health span?
Oh, absolutely. So if we actually look and use the World Health Organization, so they put out different numbers that I think are really helpful to address this. And you can look at it per country or global. And so if we think about Western countries, is that by their estimates, if you're looking at life expectancy, is that has in the last 70 to 75 years has increased. That's the 30-year mark for Western countries. But they have another number that's called health adjusted life years, right? And so that's your health adjusted life expectancy. We can approximate that as your health span. So that's how long are you able to live without a major chronic disease or disability. And in the US, that's only actually increased about 12 years. And so 30 to 12. And so we're actually looking at a sort of a lost decade within those years. And I think those are 2019 numbers. And now the numbers are starting to come in again with the newer data post-pandemic. But again, those estimates are still really holding that life expectancy versus health expectancy. We have made gains in life expectancy, but we've not made equivalent gains in that health adjusted life expectancy.
So that means in the US, for example, if we say the life expectancy on an average, if we combine male and female, is roughly, say, 80 years.
Right.
So that means out of that 80 years, a person is expected to live, the person might actually live, 68 years healthy.
That's about right, which is a scary number to really think about. And I've heard some people tell me, they're like, well, things have improved. Those two numbers are starting to come closer together. But it's not necessarily great news. Post-pandemic, as the life expectancy wiggled down a little bit. And so that's not really what we're looking for. So if we're really looking for something that can begin to affect the complexity of the human condition and human aging, is that we want both of those numbers to eventually start working together. But more than that, we really want the health that we have to sort of increase to match our life expectancy.
So when it comes to health span, what are the things that are actually reducing health span? One thing was very clear: disability. So if you cannot get out of the couch and walk, then that's a very clear definition of your health has deteriorated.
That's right.
Outside disability, what are the factors that actually affect this health span?
Such a great question, right? So disability, again, that is really at the end of the line. Is that when we think about health, it's not just our ability, it shouldn't just be our ability to get out of bed. There is a quality of health that's more than the absence of disease. And there's a quality of health that's more than just being able to leave your house or be able to maintain independence. I would say that there's an enormous amount of function that has to be maintained, this sort of intrinsic functional capacity that is really necessary for health. And that's really, it's a multi-component property. So it's everything from molecular to biologic to physiologic, and how those come together to actually be able to maintain our ability to engage and participate in our lives. And that disability is at the end of the line. And then on the way to disability, there are a number, there's really sort of a continuum of things that we can think about as health, and that these may be various events, they could be diseases. And typically when we get older, it's not just having one disease or one risk factor, it's that we actually have risk for multiple diseases, and that things tend to cluster and come together in unusual ways. And that, that for many people, you can manage different chronic diseases. In fact, I think this is one of the big things that we are learning, right? As people are able to live with diseases far longer than we ever could have. This is a biomedical miracle, right? Is the things that used to kill us no longer do. But that means that we also have to learn how to live with them. And there's some things that we can manage quite well, and that there's other things that either when they cluster together or you get too many of these either diseases, conditions, or things that can really affect our health and our function. And that when we have done some focus group work, myself and actually others at Wake Forest, Steve Krzyzewski did a lot of the leadership on this, and actually started talking to individuals about what do they want if you had a therapeutic or you had something can affect health, like what matters to you? And for most people, what they're really concerned about is getting outside, being able to engage with their family members and friends, having the physical ability to walk through a store, do their groceries, and maintain independence, having the cognitive ability to remember their shopping lists, And then for a heightened period, especially after pandemic, people were really concerned about having their immune health enough that they could interact with people. But it really comes down to a lot of that sort of loneliness and your functional ability to maintain relationships and activities. And so those are the things that lead up to disability. I think disability happens in the absence of these things. We notice them when they're gone, but that there should be an enormous amount of work really focusing on how do we maintain those activities while we still have them, rather than waiting for disability and then becoming concerned.
Yeah, so I was kind of trying to figure out, for example, if somebody had a stroke and
Yes.
Almost fully recovered,
Yes.
is that considered dinging the
Wonderful.
health span?
Okay, so this is a really open question. So this is stuff that scientists have been sitting around and we've been puzzling over. So there was a period of years in my academic life where we were actually working on a clinical trial. So how do you talk to the FDA about what would you consider an aging outcome? So if you did have a drug or a therapeutic, what would the FDA recognize and say, yes, here's an indication you have improved healthy aging or your health span. And so in that context, it was really if you could delay the time to develop a new disease. And they had certain classes, and that included stroke. It included myocardial infarction, so like heart attack. It included hospitalized heart failure. It also included things from the brain, so looking at mild cognitive impairment or dementia, or time to onset of a new cancer, or until you died. And so there was a cluster of things there that when we're looking at in terms of health span, like these are the big hairy diseases and events that people don't want, and they're terrifying. And we know that if you have a heart attack or a stroke or something, that your quality of life as a result of that is going to be really impaired, and it can be really difficult to manage and live with, and likely has effects across. And so, and we can define health span, at least for a regulatory sense, if you're running clinical trials and you're doing some of this work, one way to define it is the time until you have one of these events. Other trials have looked at it of time, how long, they call it disability-free survival. So how long you can live without having a physical or cognitive disability before you die. And so we can think about those. Those are major, big, scary events, sort of end-of-life things, and they're so important to characterize for trials. But again, they leave in its wake all of this work for both prevention and treatment before you have to experience those things that can limit your quality of life.
So that means just being diagnosed with type 2 diabetes or high cholesterol, dyslipidemia, or high blood pressure is actually, and if you can control it with the existing drug, that doesn't define that I'm in bad health span.
Which is,
yeah.
It's actually interesting. If you talk to people, those managed conditions don't register for the individual that they've lost their quality of life or their health span. It's just one more thing that you learn how to manage. And so I think, what would be ideal is if we stopped waiting for those diseases to appear in the first place and actually had a proactive system of health where you could begin doing the work to prevent them or treat them before you were just had to manage for the rest of your life. Because we know that even though, yes, you can manage, no, people don't necessarily recognize that as I've lost my health span. They have major consequences on your risk of developing some of those big, hairy, scary diseases that I mentioned before, right? Things that limit your health span, things that lead to disability, things that could kill you.
No, this is very important because my rule of thumb is until your kid goes to college, all your kids go to college. That's a personal goal. People can say you should be completely drug-free. No managing any condition. Just manage your kids.
Okay, I was going to say, some drugs are needed to manage children, so we have to manage ourselves. I've known plenty of parents who needed a glass of wine at night just to survive the onslaught of their children's lives.
Yeah, so you should be able to take that glass of wine without worrying whether it's going to damage my liver or kidney.
Right.
So my rule of thumb is, okay, so until your kids go to college, at least you should be able to stay healthy without having to take a drug every single day or an injectable every 7 days or whatever it is.
Not including coffee.
Yeah, so these are prescription drugs. These are prescription drugs. So my rule of thumb is there should not be any prescription drug for chronic conditions. So that means whether it's lifestyle, whether it's healthy eating, exercise, and supplement whatever you can, but just stay. And so roughly these days that translates to between the age of 50 to 60 because many people are having children at a later age. And then the bonus is if you can actually keep yourself healthy until your kids are married so that you can dance.
That's exactly.
In your child's wedding. Not like this slow dance, like real dance.
Like really dancing.
Really dance so that you can dance for 3 or 4 songs. So that's a lot of cardio you have to do.
Sure is.
So, and also, you should be able to enjoy the feast. So you should not have diabetes and all that stuff. So that's my rule of thumb, because that way people can actually look forward to, like, okay, so I can enjoy my child. And then the super bonus is if you can actually play with your grandchildren.
Yes.
Okay, so
absolutely, yeah. So play with the grandchildren, walk the dogs, and then would love to play with the grandchildren's child. So that would be the ultimate goal.
Yeah. So I always tell people this should be your 3 goals in your life. It's not about drugs and other stuff. Just make sure that you are healthy. So in that context, when we look at a typical 50-year-old in the US, I was looking up some numbers. It's actually immune things is on the top, because nearly 40 to 50% people have some kind of immune dysfunction, including arthritis or some joint dysfunction or autoimmune disease, food allergy, and all that stuff. So this is something that I think is preventable with managed lifestyle, not managed care. So, but when it comes to, let's go back to this health span extension.
Yes.
And then talk about different biomarkers of whether I'm healthy or not. Because when people go to the doctor, the typical biomarkers is the CBC counts, how are your white blood cells, and then the lipid panel, the metabolic panel, and maybe if you're smart enough and if you can convince your doctor, maybe thyroid, vitamin D, sodium, potassium, and then a few other regular stuff that's already in the clinic.
So I actually, I will never poo-poo the things that are already in the clinic. I think that there's actually a lot of really good insights we can get from them. If we have gotten so accustomed to looking at this marker is this disease, this marker is this disease. And I think what we're learning from aging and just health in general, right, is that we are not one biomarker, one disease. We're actually a collection, and it's complex, and it's how they interact with one another. And similar to what I was talking about before, with as we get older, we don't just experience one disease or condition. These things interact. And it's the constellation of them and sort of how they play as a system. And so I actually still do really like a lot of these sort of classic clinical biomarkers, whether they're sort of metabolic, or I do love a CBC. I think there's some really cool ones that come out of a CBC. But I think it's taking a step back and looking at them and trying to find sort of systems of change. And so I'm a big fan of looking at a lot of these biomarkers and creating composites or indices. And I think there's been some really exquisite work that has been done in this manner, whether these are things like there are a couple of metrics, one called the Clamere-Duval method, where it looks at a lot of these clinical biomarkers and other functional ones. So like one of my favorite all-time physiologic biomarkers, of course, things like gait speed, it's a vital sign, different cognitive function tests, those are vital signs for me. I think they're great. But other ones that I really love is something, how you breathe. And so there's tests, we call them spirometry, but they really test your lung function. So how hard you can breathe out. And that they really tell us so much more about just the system. So clomerbutibol takes things like this lung function measure with some of these other blood work measures and other sort of walk speed and other measures, and it collects them and it puts them into a nice index that people call their biological age. And that's actually a measure that I like quite a lot. And there's been other biomarkers similar to that. There was one that came out of the National Institute on Aging. It was developed actually by Alan Cohen. One of my favorites of all time was this homeostatic dysregulation. That's a huge mouthful. But essentially, it's that it looks at one person's measure and how far away they are from where their referent peers are. So what would a young person look like? What would this group look like? And there are some challenges in how it's constructed, but I think what it did really well that I still love is that it shows, again, it's this collection. And it's when we get older, with that complexity, there's more variability. And so it gives you this measure of how far is not just one measure away from this sort of seeming normal, but how are all of them? How far are they away from this seeming normal? And it's that spread, that variability itself, that's more important than any one marker. And so when I think about biomarkers is that I love seeing them as these collections, and that many of the ones that end up being so important for aging, they may be linked initially to a disease, but many of them really aren't. Many of them are these sort of stress response markers that are actually telling us a whole lot more than just the organ they may be tied to in a classic clinical sense.
But actually, many biomarkers are tied to multiple organs, and
They sure are.
diabetes is a clear example where your blood glucose tells you a lot about whether your muscle is absorbing glucose, whether your pancreas is producing insulin, and whether your gut is producing incretin to produce insulin.
And insulin itself, one of my favorites, fasting insulin, I love it as a biomarker of aging. It tells us quite a lot, and it's a very simple little marker.
Yeah. And then another thing with biomarker or disease markers.
Yes.
So for example, whether it's fasting blood glucose or hemoglobin A1C, when there is a biomarker, then it also comes with what you can do to make it better or worse.
Right. And so, yes, so so again, I love biomarkers as one of my favorite spaces to work in. And there's no single biomarker because it's all a biomarker for what? And so when we think about biomarkers, it's about context of use. And so if I'm looking at a biomarker, I might have one like those ones I was telling about before, where they tell you like how variable you are or how they're looking at your body as a symphony, as a collection of signals. And I think ultimately those are my favorites, no matter what they are. But again, it's what they're used for. So if I'm going to use that biomarker, again, I'm going to give a very good example. I was just on the phone with my mother. My mom she's a Spitfire. So she really is. She's awesome. She's about 75. She's in Alaska. She still works. She wasn't ready to retire. So she flies north of the Arctic Circle and she works with outlying villages. So she goes on little prop planes to villages and works with kids and families in the school districts. She loves it. And then when she's not there, she flies back to Colorado and she skis and she hikes and she loves to kayak. And I mean, she does all this stuff. But we were just on the phone before she went back to Alaska, and she was in the process of updating her power of attorney and wills and all that because she's a sensible adult who's not afraid to talk about death and disability. And so in the process of that, she said, I'm worried. You know, my grandmother, her mom, had dementia. And her onset for that was within a few years of where my mom's chronologic age is now. But my mom feels incredibly healthy and vivacious, and she's doing so much. But she asked me the same. She was like, I'm worried about, I don't know how much I should set aside. I don't know when I should start doing more regular dementia checks and screenings, and she does it pretty often. And so she was asking me what biomarkers should she do to see sort of where her risk levels are. And she wants to know, is her biologic age tied to her chronologic age? And that she's making sort of life choices about prediction for herself of when she might anticipate a slowdown. And some of it is about anticipating the slowdown, and others are she's got a bucket list as big as this room. And so, you know, she just came back from Italy and she wants to plan her next trip, and she wants to make sure she can do all the things while she can still do them. And so for her, a biomarker is that she's looking for is something that gives her a prediction so that she can make choices about her life now, not even to intervene, but just how to live. And so these are things like not even prognostic, but she wants a prediction biomarker, something now to show how I might live, how much money I need to save, how many trips I can still take. And so that's one level of biomarker. And I love that one, I think, the most.
So what did you tell your mother?
Oh, so I am making some calls for my mom. And so again, some of these are just using very simple algorithms with the blood biomarkers she already has. And then I think that there are some additional molecular markers that I'd like for her to do. And then coupling them with physiologic markers. So again, breathing through the tube, doing some simple assessments. And it's not that any one of them is important. It's that if you put them all together, you get a really great sense of where you are. And so I did give her a couple. I gave her a short list of things that I recommend, and then some blood work that we're going to do for her and go do. And I'll help her. I'll be there with her as she interprets it, because there's a lot of noise in biomarkers as well. And so it's good to be cautious. Okay, so that's one class of biomarkers. So we'll call it the mom biomarker, because that's what she wants.
But that's the secret one.
So that's a sacred mom biomarker. And then there's other levels of biomarkers, right? So maybe there is a biomarker where I am looking for an intervention, right? So I'm about to start either a new drug treatment, or, maybe, again, I came back and I've got my A1Cs out of whack and my insulin levels are off. And maybe I don't have diabetes yet, but I'm really inching towards it. And so in that case, I'm probably going to want biomarkers that are going to tell me which drug I should take and how I might respond to it. And so these are things that are going to let me know sort of how my body chemistry might react with that drug. And so those are things that we call pharmacokinetic, pharmacodynamic, so that we might be able to look at this drug and how I respond to it in the short term and make some predictions about how I might respond to it in the long term. And then I'm also going to need biomarkers. Like at that point, I'm probably going to get a continuous glucose monitor, so that I can get a really good readout every day and get lots of data to show how I am acting during my day, how the things that I eat affect my body, so that I can better regulate it. And again, using a drug to monitor that, or to manage that is only one part of the solution. And so at that point, we'd probably do a lot more aggressive biomarker testing and get a lot more data in, so that I could learn how to manage my daily life, the things I eat, the times I go to sleep, when I eat them, and when I should be taking my medication, so that I get the best, most stable response. And so that's a different level of biomarker. And then there's and those of us in the field, we're thinking about as the holy grail kind of biomarkers. And these are surrogate biomarkers. And so now that I'm on my intervention, I have my mom biomarker, so I can predict how much to save. I have I'm going to start this intervention and I'm going to monitor myself closely. And then I have another class of biomarkers that if I'm going to start taking a gerotherapeutic of some kind, and there's a lot of variety in the different classes, is that I want to know early on if that's working in me in a way that's not just managing a disease, like that continuous glucose monitoring, but is this altering the way my body is aging, so that I don't get disability, so that I can lower my risk of having a cardiovascular event or dementia or one of these. And I really want to know if this drug is working. And so that's what we call a surrogate biomarker, because I want to know quickly and responsively if this is working in me in a way that predicts the future event. And so this is what we call a biomarker that is a quote unquote mediator of that future event. And that's the space, I call it the Holy Grail, because we're not there yet. Is that what it takes to get there is you have to have both an intervention that works, that works, and you have to have some outcome over here that we call healthspan, that I think we're getting closer to defining. And you have to have both of those, and then you have to have a mountain of data from not just one person, but many people, not just one drug, but many, that can actually show you whether or not that sort of dose response that you're getting is actually accurate. And I think it's going to take probably several years until we can get that data, but I think it's worth the wait, and there's no time to waste in gathering it.
Yeah. So you wrote a nice article about potential blood-based biomarkers.
Yes.
And there are, I vaguely remember there are more than 250.
Oh my gosh, yes, there were. So yeah, we did. This was a labor of love. This is one of those things. I don't know if there are any graduate students that listen to this podcast, but if so, hang in. It's good for you, I promise. And when your advisors tell you to do something, know that it's probably harder than they're asking. You should do it anyway. But this was one of these casual comments when I was working on this trial called TAME trial, and that we had to come together and we're like, okay, we just need a small defensible set of biomarkers.
So just 1 second.
Yes.
TAME trial.
TAME trial. Oh my gosh, that is, I didn't even mention. So TAME trial, it's targeting aging with metformin. And so the metformin part, metformin's great, but the real purpose of the trial is to create an indication for aging. So again, if you went to the FDA and you did have a drug or a therapeutic, how would they know? And so the whole trial was designed to create this aging outcome. And how would you test it, is to put this design together. And part of that design, the first outcome, the one the FDA would recognize, is that clinical disease one, that how long until you get a new disease. The second was, does this drug or therapeutic, does it change your function? So your cognitive function and your risk of mobility disability, so physical disability. And then the third tier is, does it affect your biology? And so that's where we started trying to look and say, okay, we need something that, again, those three classes, the mom disease, that might help figure out who needs to go into the trial. The not mom disease, the mom biomarker determines who needs to go into the trial. And then you have the, is this drug working in me really quickly? So that's the next level of biomarkers. So are you responding? And then the third level of biomarkers, again, does this mediate that clinical outcome? And so, simple ask, as I always said, they said, can you just go do a rundown and figure out which biomarkers are out there and which ones we should include? And so that led me into one of the biggest searches of my early career, where I found more than 250 biomarkers candidates that people had published as aging biomarkers in various kinds. How many of these have been used in panels? How you have to collect them? What standards are out there? And then we did a simple filtering process. And so I looked at this mountain, and we talked to our group. We had a great executive committee, and we all talked through it. And they said, okay, well, if you had a good biomarker, how would you know? And one is, it's got to be implicated in aging, somehow links to aging biology. Two, it would be increased with chronologic age or changed with chronologic age in some way. And then three is that it should be related to mortality. So it should predict your risk of death and dying. But we are more than how long we live. We've been talking about this healthspan concept. So it should also predict health. And so for that trial, we were looking at those diseases of aging. So heart attack, cardiovascular disease, Alzheimer's, dementia, physical function decline or frailty. And so I went through and I did a deep dive in all of the literature and see, out of all those 250, we looked for the most common. We got additional expert opinions. I whittled it down to about the top 20, 30 of those, and then did a deep dive on each one of them to say, how many of these fit under each of those filtering categories? And then the last criteria is, do they change with an intervention? And that became the hardest category of all. And so what I found is very few biomarkers that existed at that time had been validated to the point that we would feel comfortable running them in thousands of people, because it's very expensive. And so we had a very short, parsimonious list that we started with. But the biggest takeaway from that entire endeavor was not the 5 or 6 or 10 that ended up being in the final. It was that there were so many that weren't, and not because they weren't good biomarkers, but because we needed better data. And so in the absence of great biomarkers, we have to generate the data, and we have to go back to the people and do the actual work to develop more novel molecular and cellular biomarkers so that we can get better predictors and we can get better mediators, so we understand whether this drug is actually affecting how we age.
So actually, when I read that paper, and I was going through all these tables. And
do you know how many months those tables?
I don't think it would be months. It would be more than a year, because there are a lot of insights and deep dive into that long table, because for each one you had at least 2 or 3 references.
Yes.
And you also had, I vaguely remember, for some, you even had the number of people in which it was tested. So
That is correct.
So I guess if there is anyone in the world who knows more about biomarker, that would be you, because you must means
Yeah.
after we are faculty or after we are in a senior position, we don't have the time to
Yeah.
go through that much literature reviews. So out of those 200, and you said that only 10 or 20
Had
actually
sufficient data.
had sufficient data.
Yes.
Do you recall any few of those 10 or 20?
I do. And some of them are because they've been used in enough population level data that we have the data for them. So again, going back to a lot of those clinical biomarkers that we think about all the time, that you see and anytime you go to your doctor, certainly insulin was one of them that came up again and again and seems to do fairly well. Good old, inflammatory biomarkers. So these are things like interleukin-6, which is a particular kind of cytokine. Things like tumor necrosis factor alpha, not just that marker, but its receptors seem to be a little bit more stable, and that those tend to associate together. There is another one of the darlings. It's one of my favorites, if you're allowed to pick favorites, but it's something called growth differentiating factor 15, so GDF15. And I'm fascinated by it because I think we honestly don't know what it does.
So which ones go up and which ones go down with aging?
We don't. I don't think we have a clue what it's doing. I think it's this incredible stress response biomarker. It's been linked to mitochondrial function. It's been linked to fibrosis. It's been linked to different disease categories. It changes with interventions, and it changes sometimes in unpredictable ways with interventions. At one point, it was thought to be a biomarker of metformin because people who were on metformin had unusually high levels of it. But typically, high levels are also associated with greater risk of disease. And so there's, again, but if you think about metformin, one of its actions is that it's a mitohormetic, meaning it kind of stresses out the mitochondria. And so if it's a stress response biomarker, it might just be reflecting it. And so it's an endlessly fascinating little biomarker, and I can't get enough of it because I genuinely, the more I read about it, I have no idea what it's actually doing.
So these four, insulin, IL-6, TNF-alpha.
I have another favorite.
Okay.
And it's one that it's cystatin C.
Oh.
And it's one of these that we typically think about it with kidney disease, but it seems to do so much more than just kidney function and kidney aging. And again, it's one of those that it's a little bit more stable. It's easier to detect in blood, so I think it behaves pretty well. And it's often really in studies that we've done is we found really tight associations between cystatin C, GDF15, and those tumor necrosis factor. And so again, even though we think of them very different, is that they seem to in concert tell us more than any one biomarker alone. Others that I'm fascinated with, red cell distribution is something you can get from your CBC. Other cell counts that come up. I mean, there are so many various markers that I think the important part is any one biomarker alone is not sufficient. It's how they come together. And then there's enormous work coming out now. I love watching the space around, proteomics and within methylation and seeing sort of how people are constructing these more molecular level biomarkers. It's still the same principle. It's how do these things play in concert and at different levels, and they begin to integrate over time, and so that we can see different emergent properties as different levels of complexity increase.
But out of this, your favorite five?
My favorite five, yeah. So those are my favorite five, yeah.
Out of this favorite five, I think 3 or 4 of them you can get your doctor to actually write the...
That's right.
Because insulin you can get.
Yep.
I actually get my insulin reading.
Yeah.
I don't know about IL-6 and TNF-alpha.
Yeah,
but
maybe.
cystatin and red blood cell distribution, GDF15 also, I don't think.
No, that would be hard to get your doctor to get.
Yeah. But it comes down to the same concept. Even when we go to our doctor's office, it's not one test that tells us our health. It's a handful of tests. So that's why people have to be open to this idea that when it comes to aging, there will be multiple tests.
Yes.
And just like you said, GDF15 is one example where its levels go up, but doesn't necessarily mean that it's bad. Similarly, IL-6, actually when we exercise, our IL-6 levels go up.
They go up. That's right. It's also a myokine. You're absolutely right.
Yeah. So these things also have to be interpreted accurately.
That's
with the
right.
So, the reason why IL-6 and GDF-15, these have not yet been clinical biomarker, because there is a lot of work that goes on behind the scene. Like even hemoglobin A1C, it's a very recent biomarker for type 2 diabetes, right?
That's right.
So it took a lot of years.
Huge number of years in order to get it validated and established. Even many of these, even when we're looking at our blood lipid levels, that so many of us now go to the doctor and we expect to see them and we go get a statin and we look at this. Establishing those as biomarkers, there's a huge legacy of work that led to that. And even so, we still look at those levels and don't know exactly how to interpret them. And I think that that's great. And actually, so I think this is one of the myths I would love to dispel, is that, again, there's not going to be any single bullet that changes our aging. There's not going to be any single marker, because we're complex. And I think that it really is, it's these symphony markers that I think are really both how we live, how we react, how we respond. And that, that essentially comes down to, how am I handling both damage and repair? How resilient am I in the face of stress? And so any of these markers that sort of get that complexity, those to me have the most utility. And the same with therapeutics. We're complex. It's not going to be any one drug that works for everybody. It's going to be, again, you go back to this, no drugs for as long as you can, and do all of the things that your grandmother told you to do to begin with. and small hacks of things that we should know but somehow forget, like about timing our eating and lights.
Healthy grandmother.
Yes, and healthy grandmother. Yes. And then these are the other things that help give us signals within our body about how we respond.
But actually, when we look at interventions that have proven somewhat to reduce the rate of aging or aging-related stuff, there are very few handful of them. So among lifestyle, maybe calorie restriction is one that has a long history.
Yes, it does.
And maybe exercise. I'm not sure whether there are exercise interventions to reduce the rate of aging. You are in the field, so you might know much better.
That's a hot topic, and there's no way I can answer that without angering someone.
What are the other lifestyle interventions?
So I would say the biggest lifestyle interventions that we see is, again, caloric restriction or food clocking of some kind. So whether that's restricting total calories, changing the timing of calories, and then I think that those
have not been done on people over the age of 65.
You're right. Anything that affects calories on that age is really challenging. I mean, whether you're talking about it with a dietary intervention or even these newer classes of GLP-1s, right? Anytime you induce weight loss in older age, this was some of the trial work that I had the great fortune to be on before coming into XPRIZE, which I know you are familiar with, is that when you induce weight loss in older adults, is yes, they lose weight, but they also lose muscle mass. They also lose bone mass. And if they cannot maintain that weight loss and they increase their weight again, they regain as fat. And they don't regain the muscle, they don't regain the bone. And so there's a lot of conversation around at what point does the stress of the intervention and the potential long-term consequences, if it can't be maintained, if it's not a persistent change, is it might you be putting that person at more risk. And so I think some of the conversation, especially around behavioral interventions, is if we start them too late, and that it's not a patterned, ingrained behavior that they can maintain through lifetime, is that we really need to evaluate those effects.
So then among pharmacological interventions, we started this with TAME trial.
Yes.
So let's go back to metformin and what are the clinical studies that have been done so far and what's going on now?
So metformin is a really interesting drug. And I think that, I became really fond of it because of its public appeal. Is that it can be given roughly at the time when we started this trial, it was about a penny a pill. And so even if it wasn't perhaps the most effective drug, if you could give it to a large number of people and it would have great public health appeal, even if it had a small effect. If you could delay diseases with one drug, that would be great. And so that was the great concept. And now since then, is it the only or perhaps the best or most effective? Huge questions around that. And so there's a lot of people looking within the space. And I would say that there are different camps of therapeutics that seem to have great effect. And so there are things that are work in that sort of nutrient sensing and metabolism world. So again, that's going to be like the metformin. It's also going to be things like rapamycin, so things that target mTOR, so mTOR inhibitors. There are also things within those energetic pathways like NAD metabolism. Anytime you can affect that NAD metabolism through various ways is that you're also affecting that nutrient sensing, how your cells detect whether they're hungry or not, and what they're storing and how, and sort of how they're metabolizing nutrients. So that's one class. Then we have a lot of people that are working in things that are around inflammation and immune health. And so whether that's using the immune cells as the therapeutic delivery device, doing gene therapies or other things to, again, use those cells, or doing things that alter or affect somehow our inflammation. And so there's a huge classes of these that are coming out, some really interesting ones, and we'll be seeing how they affect. Closely related to those, there are things that affect what we call senescent cells or senolytics that, again, also have effects on inflammation. There are additional classes of drugs that look at how we fold and misfold proteins and affect those. And so you have all these different clusters of areas that people are developing because they've at least shown in animal models that if you affect these pathways, if you aggravate them, animals live less long. And if you ameliorate them in some way, animals live longer. And now trying to translate those into humans and still get the same effects, which typically in humans, the effects would be blunted, as would be expected. And that sometimes in humans, the most effective drugs have the greatest side effects. And so having something with the best effect is not always the best strategy. I think one great example going back to metformin is this metformin and fenformin. So there was a version of there's a biguanide just called fenformin. And it was originally used because if you looked at its pharmacokinetic and pharmacodynamic data, is that it was far more effective at lowering blood glucose in humans than metformin or any other biguanide. It was great. And so people took it straight in. It's going to be the next amazing type 2 diabetes drug and expect to have all these effects. Unfortunately, it was too effective and it actually increased the risk for lactic acidosis and kidney failure and acute kidney injury. And so when we're thinking about things for aging is you have to balance the risk versus the potential benefit. And sometimes the thing that's the most effective in animals and really effective short term, if you start magnifying that out over years and in different people, the effects can be disastrous. And so again, it's just, I'll caution anyone going into this field is be patient with it, is that you might turn on the news and this one's good for you and then it's bad for you. And then it's good in this population, but it's terrible in women. And, and that humans are complex. And that we should expect that and have a certain amount of tolerance. But I know it's even hard to have that kind of tolerance as scientists. And so I know that the public has to really go along the journey with us, is that we're all going to have to figure it out together.
So metformin is supposed to be relatively safe because it has been taken by, I think, close to 1 billion people now.
A lot of people.
Then the next things are rapamycin and then the senolytics. So what's happening with those two?
Yeah, so I would say they're both still in broad development. So rapamycin is actually an mTOR inhibitors because there are different classes of them, and there's new ones that are coming out in different mimetics that actually reduce some of the side effects that are common, is that they keep progressing. So it's really pretty incredible, is that we're getting a lot more insight into how they could be used safely and by larger numbers of people.
And then senolytics.
Senolytics, oh goodness, yeah. So I had the, again, for graduate students. When your advisor tells you, could you just know that it's typically harder than they think, and it's harder than you think, and you should do it anyway. So I was naive enough and really fortunate enough to be at the right place at the right time. So when we were actually looking at how to take these new class of drugs called senolytics, and they had great evidence in mice, and how do you translate them to humans? I just moved to Wake Forest, and I was part of this translational Geroscience network. And that we're like, okay, well, we need a use case for the network. We'll take those, we'll test them at Wake Forest, we'll bring them up to trials. Actually, initially, I thought we were going to take them to non-human primates, and then it turned out that it was faster and easier because they were repurposed drugs. We could go straight to humans if you found the right sort of disease condition. And so we really were looking and trying to pair, because it's a new class of drug. These senolytics, one of them was a chemotherapeutic agent called dasatinib. And that it happened to, in culture and in animals, be particularly effective at targeting and inducing apoptosis in cells that were senescent. So these were a particular cell type where they stop dividing, but they also have a big change in their gene expression. They change in the number of different inflammatory signals that they put out, and they end up having major consequences both in the immediate cell area that they are in, and then also systemically when that gets into the bloodstream, and it affects the whole body. And so these were particular classes of drugs that could target those cells and basically take down, because these cells, they're like cancer cells. They don't want to be defeated. And so they just linger around much longer than they should. And so what these classes of drugs would do is that it inhibits that sort of protection hardware, basically. And so if you pull that down, then the cell can be subject to apoptosis, right? So that it can be destroyed and cleared. And so that was the general thought. And so we took that into humans for one of the first time. And we did that in a rare disease called idiopathic pulmonary fibrosis. And again, it was a fatal disease, ultimately fatal disease, less than 4 years survival time after diagnosis for most people. Really, really terrible lung disease. And importantly, it had key features where it had a lot of these senescent cells, had a lot of those same kind of properties, and that had shown in mouse models of that disease that this drug class was really effective. So we took that into humans, and I would say it was a very challenging early trial to run.
How many people you had?
We had, in the first trial between Wake Forest and our other site at San Antonio, we had to bring San Antonio on because we didn't have enough people with IPF in our population. And so we ended up, in that very first trial was an open label trial of 14 people. And then immediately towards the end of that, right when we went around to publishing that work, is that we knew that we needed to get a control group as well. So we doubled it and brought in sort of another cohort of people. And the challenges were many, is that it was very short term. We were looking at intermittent drug administration. We had to see if they would tolerate it. We had to put together a whole new battery of tests to see how it worked. We needed biomarkers of cell senescence because we actually didn't have any for human trials. And so that was another problem that we found going into this. We had no way to monitor it.
Because the disease is in the lungs.
The disease is in the lungs. And so, but if we're targeting cell senescence, is this systemic? Is the level of senescence in the lung, is it reflective of the level of senescence around the whole body? And so we honestly didn't know. So the entire trial was like a lesson in figuring out how much we still had to figure out. And so for me, I think it was one of the most useful reasons to ever run a clinical trial, is that it teaches you the questions you should be asking before you go to bigger trials. And so now out of that, there's this whole senescence mapping network that's come out. They call it SENNET, the senescence network, looking at spatial biology. Where do they exist? How do you target them? If you do target them, what happens with the therapeutic? What happens when you aggravate them? And it's led to an enormous amount of work that really needed to happen. That again, the therapeutic in this case, one part of it has potential and promise, but another part of it is this entire area of biology that we actually needed to better understand.
Yeah, so now there are quite a few senescence trials, right?
That's right.
For other diseases.
There are, yeah. And so they're showing really great promise. I've seen some really impressive work coming out around Alzheimer's disease. And again, that they do pass through the blood-brain barrier, and that there has been some really interesting work coming out to suggest that they may have effects there. So, time will tell if those can expand
This is human study?
These are humans, yeah. So they're being tested in humans. So looking at Alzheimer's disease, I think early onset and to see what happens. But again, it is very suggestive, and there's some really excellent groups working on it right now. And it's not just with the 2 drugs that we had started with, but there are other groups that are developing more novel approaches and more refined approaches that might have fewer side effects. Because in our trials, we did see side effects. They're very well published. This was a chemo agent. So, nausea, headaches, those things, they were present, but we expected them. And in this case, with that patient population, they didn't mind if it would possibly affect their disease prognosis. Yeah.
So what are the other supplements or other stuff that is in the pipeline? Or means now you have such a global view.
So much. So it's great. So now I'm running this prize, and I get to see what everybody's working on, and it is the most fun I've ever had in my life. And so I get to see and talk about, and we have everything from various lifestyle approaches coming in, different combinations. Really hot area. It's got the whole world buzzing is around partial reprogramming. It is, one of the biggest, hottest areas now is to see when and if those will translate to humans. So this is taking a cell that is differentiated, so like a normal adult cell, and that you can express certain transcription factors that, and its original, the Yamanaka factors, it takes it back to a state where it can differentiate into other cell types. The partial part is it takes it back, not so it can become like, you don't want your muscle cell to become some other cell. It's not really healthy for humans. And so the idea is that you would take that cell back to a state, not just so that it can become another cell, but it's partial, so that it at least on the epigenetic side has been somewhat reversed or rejuvenated. And so now there's a huge field to say, okay, if you do that, what are the consequences of that? If you do that in particular cell types, can it carry out? And it's a really hot area. Other areas, we have different therapeutics coming in, RNA therapies, various gene therapies that are being used, anything targeting the immune system. There are whole worlds of like transplant, which is really cool, and it's a wild, wild area. Anything, I think one of the very earliest in transplant was like an ovarian transplant. Oh. And this has been like, I think more than a decade ago, and at least in animal models. And so, there's a whole world of regenerative medicine that could be employed. Think about, growing replacement parts. Who knows? Yeah. I mean, when we think about the future and where we're going to go, and that some of that may feel scary for aging, but if you think about it in terms of if you're waiting on a transplant list, the possibility of having an organ that is grown to your needs using your cells that you're less likely to reject, it's an incredible possibility. Even if it's not here today, what could that mean for us in the future?
Or maybe take a organ that's already donated, but it's not meeting the quality.
That's right.
And if we can partially reprogram that organ.
That's so exactly right.
Is a younger heart, so that
so this is again another really huge area that people are working in and developing. It's fairly incredible.
What about the simple transplant of blood transfusion?
People are working on it. So again, it's whether you do plasma transfusion or other transfusion. Other people are actually just looking at the factors within the blood, and that you might be able to identify different therapeutics within that without having to go through the whole messy transplant thing. So, there's a lot of clever approaches. And I think the bigger point is that it's not going to be any one of those that's likely going to be it. And I think, especially when we get into aging, I go back to this symphony, this complexity, is that it's going to be figuring out which intervention at which time and in which person. It's how do you personalize the approach? How do you cater it once they're on? How do you understand how it's working within that person and whether they can maintain it? And so in this way, I think it's not going to be one thing, but it's going to be the combination, and it's going to be possibly digital medicine and monitoring how we do this. And probably actually starting a lot of it sooner than we think we should, and actually being proactive about our health and what we're going to do for healthcare.
So now it leads to your current job. XPRIZE.
Yes.
And the Healthspan XPRIZE. Tell us a little bit about it.
Yeah, so XPRIZE Healthspan. So again, I left academia to run this. I got cold called So I was in my lab, was actually preparing my promotion materials. Everything was going good. I had my studies, I had my group, I worked with great people, I loved Wake Forest, we had great studies. And then I got this call to do this crazy thing. And that this group, a nonprofit foundation called XPRIZE, had raised over $100 million to basically run a prize to incentivize people around the world to do exactly the work I had been doing. And so what this is, it's a global competition that we award $101 million over the course of 7 years as a global competition to find teams to accelerate therapeutics that can affect aging biology. And so that team that wins has to demonstrate that their therapeutic within 1 year can restore muscle, cognitive, and immune function. And it has to do this in trials in people who are age 50 to 80.
50 or 60?
50. We actually dropped it down based on, because this is, again, we're running a global competition.
Yeah.
So unlike running a single trial, is that we actually put our design out to the world and asked people to beat it up. One of the key feedback that we got from people is they came back and said, well, yes, but if we want this to generalize, people are asking for these therapeutics at the age of 50. What if we have somebody who's maybe less healthy, or we can use these biomarkers to determine that their biologic age is not their chronologic age, and we would start the intervention there. And so we decided, well, we're going to let the innovators innovate, and we'll open the age range to at least 50. And as long as they can justify who they're going to test it in, we'll let them. Because otherwise it was awful ageist of us to assume that this is when you should be taking these therapeutics.
So now it's 50 to...
So we dropped it 50 to 80. And so now we have to do the work of actually, within each of these trials, is that they're based on personal response thresholds. And so for any individual, they're going to start on their intervention, whatever their team decides they have to do. And that they'll take that for a year. And then at the end, we're also going to follow it up. And they're going to use their personal response threshold. So how much does that person have to improve in muscle, cognitive, and immune function to say that they are better? So, and no longer looking at people as averages, is that I don't know that that's necessarily the right model for early stage clinical trials, especially in aging when we're all quite different. Instead is saying, if you ever went to your doctor, you would be looking at your own personal levels to say whether you had gotten healthier or that this thing was working or not. And so now we're applying the same thing into a trial setting, but globally. So each team has to figure out, they'll recruit maybe 100 people in the finals for those finalists that go through, and they'll do that, and they'll have each person. They're going to do whatever their therapeutic is. We just set up the system. We set up the baseline. We set up the follow-up. They have the protocols they have to follow. And otherwise, it's up to them.
And these people can have any coexisting condition?
It's going to be up to the team to determine how that looks. So we would say as long as that coexisting condition is well managed.
Yeah.
And so if somebody has terminal cancer, probably not the best strategy to try a new therapeutic for aging if there's something there. Or there could be any number of other sort of conditions that we don't want just disease treatment. Like it really does, you have to affect the biology in some way.
So how is this prize selection process going to work?
This is great. So we're about a year in to we started with a public call. And now we're in what we call primary registration, where we have our more serious teams that are registering, submitting their materials, and that's going to go through the end of 2024. Actually, December 20th is our official deadline, but we do have a little wiggle room for teams who need it. We just won't be manning the hotlines over the holiday week, so we're trying to get people to get done early.
So that you can read all those proposals.
Right, we're going to have all this time over the holidays to read all those submissions. And right now we have, I think as of today, 469 teams have pre-registered around the world, 53 countries, 6 continents. And out of those, we expect qualifying submissions. This is like a 12-page submission about what they're doing and how. We expect about 100 of those to come in that will really review carefully and we'll have an independent panel of judges, and they're going to select the top 40 teams. Those top 40 teams get some award amount, and they're called our semifinalists. they have to take the next step and actually do something in a small clinical trial, maybe 5, 10 people, whatever they need to show that they're ready for trials. We'll evaluate those, and in 2026, we'll announce our top 10. Those top 10 then have to go on and run that 1-year clinical study to show that within their persons and their trial that they're able to have enough people to respond to their intervention to meet our criteria for muscle, cognitive, and immune function improvement.
And that trial has to have roughly 100 people?
Roughly 100 people.
And randomized to?
Randomized is still important.
1-to-1?
We are not mandating 1-to-1 because it will depend somewhat on their therapeutic, their population, and their design. So we're trying to leave as much flexibility to our teams to innovate as they need to while still meeting the demands for us to be able to judge them.
I see.
Yeah.
And then, so what is the criteria? How much they have to improve?
Oh, this is hard. So the criteria, and we've said it is very rigorous. So we're setting these to within each person. They have to meet some response threshold. And the response threshold is equivalent to what we'd anticipate would be and they have to exceed a 10-year, 15, or 20-year magnitude improvement. And so this is looking at a referent population. You would expect in a similar kind of group, how much would you expect that person to decline in 10 years, 15 or 20? And then you just flip that. That's the magnitude they have to improve. So it really is going to be incredibly, incredibly challenging to win. These will not be just sort of spontaneous, that somebody sort of magically gets better on their own. So, I mean, it really is going to take it's going to take a very strong stimulus and a very arduous approach for the team who's actually going to go in and make it happen. But we're otherwise not setting any limits on the teams for what they can bring in. It can be a lifestyle. It can be one of those newer therapies that I talked about. It can be a repurposed drug. It can be a digital medicine tool that helps you personalize what the approach is or helps people adhere to whatever the approach is. It can be any combination. Is that I think what we've decided is what we need are solutions, and that we're not going to limit the solution space in any way.
Okay, so let me play a game.
Of course.
Okay. So, for example, these days, GLP-1 receptor agonists have been extremely beneficial. They have multiple benefits, including immune system. And they can also reduce sleep apnea, which can affect cognitive function.
Sure.
Suppose say I start a trial. I recruit 60 to 65-year-old who BMI above 30 so that they can qualify for GLP-1 receptor agonist.
Sure.
And they do have some type 2 diabetes or one of these coexisting conditions. And GLP-1 receptor agonist in 1 year actually does quite significant weight loss. And if they're paired with exercise, hopefully they can keep that muscle mass.
Yeah.
The immune function will improve. And their cognitive function might improve. So by selecting a pretty specific cohort.
But if you can demonstrate it, if you can demonstrate it, how wonderful would that be?
But that GLP-1 receptor...
I also don't think it's going to be as easy as people think with something like a GLP-1 receptor agonist. Is that one of the challenges, right, is that you not just want to maintain muscle mass, but remember that's also improve. And so you have to have some kind of a muscle stimulus that can not just prevent the not just attenuate the expected declines, but you actually have to improve. And so the amount that's going to be required to offset that is going to be fairly dramatic. But if somebody can unlock it and figure out how to do that without without side effects, even in that patient population that they've sort of selected, again, it's how it's defined and how it's used. But if someone can unlock it, think of the potential for others. Yeah, and so we are not going to say no. We need solutions, whatever they may look like.
Yeah, because, these days nearly, 40% of US adults are obese. So they will meet the criteria of GLP-1 agonist. And in this conference, we are both attending this Gerontological Society conference in Seattle. And actually, there was 1 or 2 talks about GLP-1 receptor agonist being a protector. So that's why I was bringing up this issue.
No, and so GLP-1s has been one of the hot topics. People do ask, you're like, oh, you're just going to give it to the GLP-1s. And I'm like, well, no, they're going to have to work for it like anyone else. But if somebody wants to come in and do that, great. Metformin, it's the same thing. People say, oh, well, what about metformin or some of these others? I'm like, I think it's a great preventive. But if you can figure out a right population, right stimulus, right coupling or combination with something else that you can suddenly show improvements within a year, more power to you. Go for it. But I think right now what we have is, I don't think we have a clear winner yet. And I think that's what makes it the most fun.
So that means you're actually constantly looking at the submissions that are coming in.
Constantly. Constantly. And to know that, that it's gaining really global attention, which has been exactly what we want, both from individuals, from regulators, from large pharma companies too, that are just interested to see like who's doing what's happening. And that it's not isolated to that. I think there's a lot of approaches, and people are getting very serious for one of the first times, is that you have some of these big companies that are developing really novel things, and that they're looking at it, they're like, well, but if I want to win, we got to combine it with lifestyle interventions. And so I think it's starting this conversation where it's like, if you ever went to your doc and said, hey, I think my biologic age and my chronologic age are off, and they were just like, well, take this drug. That's not really what it's going to be. It's going to be like, how do you thoughtfully approach this in a way that people are going to want to adhere to, and then to be able to couple with whatever their lifestyle intervention is. Again, could be sleep, could be light, could be diet, could be timing, could be exercise, and that we're incentivizing people to figure out the complexity of human aging and intervening.
And then if there are two, just like you said, someone is proposing a drug, and someone else is proposing a lifestyle that may synergize with the drug, are you also going to ask them to work together?
We are not going to. Again, this is so much fun. It's like I had no idea this world existed. So as an academic and as a scientist, I'm used to controlling everything. In a prize competition, control kills innovation. And so we're just not saying no. Is that if we let people compete, they can merge, they can choose to form one super team. They can choose to, I think my approach is slightly better than their approach, and we're both just going to go for it. But we let people really decide what they'd like to do. I would encourage merging in that situation, and try to do whatever it takes to actually improve the chances. Because again, a win isn't just giving away the money. The win is, do we have a solution that can actually impact human aging, that we can implement in real time and make a difference? And I would always incentivize that.
But when it comes to aging and disease, there is sex difference.
Of course there are.
Is there? And most of it, when it comes to many clinical trials, if you look at them, some of them are biased towards male, some are female. Is XPRIZE doing anything to address that?
No, so this is a great question. And so we talk about this, if you could know how many hours we have talked about this amongst our scientific advisory board and during development. And so sexual dimorphism is one of the most well-known parts of any intervention on aging. So if you look at lifespan across species, it's absolutely. Most of the things that are coming out of the National Institute on Aging Interventions Testing Program, which is like a multi-center trial for mice. Almost everything either works in females or it works in males, but not both. There are very few exceptions. Caloric restriction can often work in both sexes, and things like rapamycin can work in both sexes, and a handful of other things.
Metformin?
No comment. For one, metformin and the ITP had no effect on lifespan. So there have been other studies that show that might have some health effects, but not lifespan, not on the ITP. Again, sexual dimorphism is known. and it's common and it's expected. And in humans, we expect it. We know we expect it. We're not asking people to demonstrate that they have effect in males and in females. But we are saying that you have to conclude both males and females in your trials, and that the collective effects are what we're looking at. And so these can't be trials that are only run in men and only run in women. But could there be a personalized approach? We're not limiting it. And so if you can figure out which way that needs to be personalized, fine, go for it. But there's a whole other world where we actually have to figure out really the sex and gender-based innovations and therapeutic solutions. And so in the future, we have a new prize that'll be coming out that's really focused on ovarian health, and sort of looking at solutions that affect the ovary to impact health. Not the ovary for fertility and reproduction, but the ovary as an organ that has really major systemic effects and is ripe for its own therapeutic interventions.
Yeah, I mean, in mice, we have seen that if you
That's right.
ovarectomize a mouse, then it has multiple adverse effects on different organs.
Absolutely.
So keeping that ovary healthy as long as possible will actually easily increase health span.
Exactly right. And as we learn when we affect the ovary, how it affects health span in women also will give us a lot of insights about disease development in men. So understanding those actually gives insight for both sexes.
Yeah. Anything else going on with XPRIZE?
So those are the biggest ones. So again, we have this huge Healthspan prize. We've just started it. We've got a big runway, and we invite everyone to follow along. The next biggest was going to start development the next year is that we have something we call the XPRIZE, and that's the one that's focused on ovarian health and function across the lifespan. And so we have a development team that's just starting out for that one to see what would that prize look like in the future, and hoping for a launch later in 2025. We have additional prizes, things that might affect the brain, looking at novel tech and solutions. We have a lot of other things, so we're always active. And so I not just run the Healthspan prize, but the health domain is what other prizes or areas that could be incentivized that require a breakthrough. And so typically for these prize concept areas, they're areas that are under-resourced, don't have the right sort of public attention, have major barriers that people are not collaborating in a way to make a difference, and are sort of key global challenge areas, whether again, that could be brain health and aging, things could be around mental health. We're looking at women's health. Aging is a very big one. And so, any of these sort of solution space that really need to be advantaged, that we think we can do it through running large scale science and technology competitions.
Yeah, this is exciting because these type of competitions means if we look at the history of XPRIZE, I think the first one was the space flight.
That's right.
Yeah.
That's right.
And then now we look at space flight, it's now, initially the billionaires were thinking of going to space. Now even the millionaires are beginning to think because...
That's right.
A few years ago, I was talking to somebody who used to manage the International Space Station. And I asked him, what would be the biggest breakthrough? And this person, it must be 12 years ago, he said the amount of money we spend to lift off 1 kilogram to the escape velocity, that's pretty high.
Yeah.
If we can reduce it to less than $1,000, then that will be a breakthrough. And then I asked, how do you reduce that? And he said, if you can recycle the rocket. And 12 years ago, this guy, of course, he was involved in ISS, so he knew how much money goes into what part of the space program. And recently, it was really nice to see that, yes, we can bring back the rocket. And that was something that was almost unimaginable 15 years ago.
Wow.
So now, hopefully this XPRIZE will inspire not only one winner, but because I think out of the 40 ideas that you'll get, 10 or 15 might actually work in specific patient population.
So I agree. And so what got me out of the lab was not to give away money. It was actually one, to build a framework around how would you test this. And there's a lot of the intellectual work behind that and forming groups. But the biggest thing that got me out of the lab is, again, I keep talking about we need this data to develop biomarkers. We need this data to find new drugs. We need this data to figure out personalized approaches. that data doesn't generate itself. And so again, looking at the impact of a prize like Healthspan is suddenly, once we get to finals, we're going to have 10 trials that people around the world are going to run and patient populations that we're not going to define for them, and that they're going to have to use a common protocol book. And we're going to be gathering longitudinal data on various interventions. That data is the resource. More than any one trial, more than giving money to a team who wins with the best solution, or having sort of the commercial runway for them at the end. It's creating that data set so that you can then go back and you can begin to validate the biomarkers, that you can find new mechanisms that might actually be better linked to those changes with response to that intervention that you saw. That you can start to find what biology is paired best with that therapeutic that you can uncover on the back end. And you don't get there without actually generating the data and doing the work. So this is a prize that it's a vehicle for impact. And so we can develop methodologies, we can get new solutions, and we can actually drive science forward in a big way.
So that means the 10 finalists, we're going to have 100 people each. So that's 1,000 people.
That's right.
And you are developing a framework so that all their biosamples come to one place for analysis?
One or regional spaces.
I mean, they'll be combined so that you will actually, So at least from the control people, you will also know what are the biomarkers that correlate with aging and then what these interventions are doing.
That is correct.
That's the most important outcome that people are not thinking about, because that will be hugely.
That is what pulled me from academia to lead this. Is that it's very similar to the work that we were already doing, but now to do it at a global scale. And in a way that actually is not just for academics, but it's commercial and academic and anyone in between. The idea could come from anywhere.
No, this is brilliant, because almost 10 years ago, from our lab, we developed this app called My Circadian Clock, and it was developed for a very simple reason, to see when people eat. And then now we have run at least maybe 8 or 9 clinical trials on this using the same platform. And from people from Australia, Europe, US, India,
powerful.
and all of this. So now, as we have grown, we realize that we have at least 1,000 people's 2 weeks of CGM and food diary, spanning different age, both genders, different ethnicity, and also shift workers, regular workers, people who are going through cancer treatment, or those with metabolic syndrome. So I understand the power of this collective data.
This is it. This is exactly it, is that it's a vehicle for crowdsourcing in a way that you can't necessarily crowdsource, especially when it's, you're looking retrospective and you ask people to submit their data, then the data is kind of collected anyway. But if you have a common platform, all of a sudden now you can make comparisons, then you can dig deeper, then you can get an actual understanding.
That's super exciting. So hopefully, maybe in 24 months, you will have the 10 finalists, or at least we'll know the 40 semi-finalists in 6 months from now.
That's exactly, we will.
So that will be really exciting to see what are popping up from. I guess there will be at least 550 applications, because all the academics, they submit just 10 hours
on the day of. They do. And we expect it. We're ready for it. We're ready for you.
I have submitted one grant 10 minutes before the deadline, so I know.
It's what we do.
Thank you so much, Jamie.
This was
exciting, and sure, I'll touch base with you in 6 months or so to figure out who are the top 40.
Oh, it'd be great. We're going to be doing the announcements in May. So we'll have like an investor summit and a big milestone awarding. But if you want to come in and do a rehash on sort of who came in and what the data looks like, and I would love to.
Awesome.